let's talk about one of the most powerful and most hidden pieces of tech on the entire planet, the gigantic engines that make global trade actually happen. And look, these are not your car's engine, not even close. We're talking about true mechanical titans, and understanding them is this incredible story of power, pollution, and some seriously brilliant engineering. Just think about it for a second. Pretty much everything you own, your phone, your clothes, maybe even the food you ate today, it probably spent some time on a massive ship just like this one, crossing an ocean. These vessels are the absolute lifeblood of our economy, and they move because of diesel engines so enormous they could literally power a small town. But all that power, well, it comes with a price. For decades, what came out of those giant funnels went completely unregulated, just pumping pollutants straight into the air. And that has led to a really critical question, one that's kicked off a whole new wave of engineering. How in the world do you clean up the most powerful engines on Earth? So to figure that out, here's our game plan. First, we'll break down the pollution problem itself. Then, we'll look at the new rules that forced everyone's hand. We'll dive into the amazing toolkit of technologies engineers came up with, weigh the pros and cons of each, and finally, we'll take a look at what the future of ship power might hold. Okay, so first up, we have to get a handle on the problem itself, because it's not just about, visible smoke. It's about very specific and harmful chemical compounds that get created inside these massive engines. The main villain in this whole story is a group of gases we call nitrogen oxides, or just NOx for short. Now, what's really interesting is how this stuff gets made. When you compress air inside one of these huge diesel cylinders, it gets incredibly hot. We're talking way over 1,300 degrees Celsius. At that temperature, the nitrogen that's all around us in the air, which is normally totally harmless, it literally starts to react with oxygen, and it forms NOx. The simple brute force reality is, the more power you make, the more NOx you create. For a really long time, this was just seen as the cost of doing business. But as the world got a lot more clued in about what air pollution does to our health and the environment, well, something had to change. A global crackdown began. The big moment really came when the International Maritime Organization, the IMO, stepped in. They brought out a new set of rules called MARPOL Annex 6, and this was a huge deal. For the first time ever, there were global limits on air pollution from ships, and they were specifically going after pollutants like NOx. And these rules just kept getting stricter. Tier 1 back in 2000, that set the first baseline. A decade later, Tier 2 came along and demanded about a 20% cut from that. But the real earthquake was Tier 3 in 2016. This wasn't just a small step forward. It was a giant revolutionary leap. Just let this number sink in. 80%. To meet that super strict Tier 3 standard, engine manufacturers had to figure out how to cut NOx emissions by a whopping 80% compared to the engines they were building just a decade and a half earlier. I mean, you can't just tweak a design for that. This required completely new technology. Now, these incredibly tough Tier 3 rules, they don't apply everywhere on the ocean. They're only enforced in these special zones called emission control areas, or ECAs. And that makes sense. These are usually the busiest coastal waters, where ship pollution has the biggest impact on people, places like the coasts of North America, the Caribbean, and Europe's North and Baltic Seas. So, you're an engineer, you're facing this massive 80% reduction target. What do? Well, they had to get creative. They essentially came up with a toolkit of 3 completely different ways to solve this NOx problem. So let's take a look at how each of them works. The first strategy is, in concept, pretty straightforward. The idea is, okay, let the engine make the pollution just like it always does, but then we'll clean up the exhaust fumes after they come out, before they escape into the atmosphere. You can think of it like an after-treatment system. This is done with a system called selective catalytic reduction, or SCR. So let's walk through what's happening here. You can see the main engine producing power and pollution. Now follow that red exhaust pipe. Instead of just going straight out the top, it gets rerouted into this huge box, which is the SCR reactor. It is basically a giant, high-tech chemical treatment plant for exhaust gas. The chemistry behind it is actually pretty clever. They spray a urea solution into the hot exhaust stream. That intense heat turns the urea into ammonia. This whole mixture then flows through a special material called a catalyst, and that triggers a reaction where the ammonia and the harmful NOx basically break each other down into completely harmless nitrogen gas and plain old water. All right, the second approach is totally different. Instead of cleaning up the mess after it's made, the philosophy here is, why not stop the mess from being made in the first place?
This is all about changing the actual combustion process inside the engine cylinder.
This is done with something called exhaust gas recirculation, or EGR. If you look at the diagram, you can see how a little bit of the exhaust gas is siphoned off. It gets cleaned and cooled, and then it's mixed right back in with the fresh air that's going into the engine. By adding this inert exhaust gas, you actually lower the peak temperature inside the cylinder, keeping it just below that critical 1300-degree point where NOx forms. No extreme heat, no NOx problem. Okay, now for the third solution, which is easily the most radical. This one involves throwing out the traditional fuel and the traditional way the engine works and starting over with something completely different. So your traditional ship engine runs on the diesel cycle. You squeeze air until it's scorching hot, then you inject fuel and you get a very hot explosion. But some newer engines can run on natural gas using the Otto cycle. With this method, you mix the air and natural gas together before you compress it. Then a tiny little squirt of diesel fuel acts like a spark plug to ignite it. This leads to a much cooler, cleaner burn that produces so little NX, it can meet the Tier 3 rules all by itself. So we've got these three fantastic solutions. But as with any big engineering challenge, there is no single best answer. When you're choosing which technology to use, you're always dealing with a complex set of trade-offs. And this table really lays it out. The CSER system is very fuel efficient, but boy, does it take up a lot of space, and you have to keep it supplied with urea. Then you have EGR, which is more compact, but it does hurt your fuel economy a bit, and it requires its own chemical, caustic soda. And finally, the natural gas engine. It's fantastic for NOx and sulfur, but it comes with its own environmental headache called methane slip. And that brings us right to the future. Solving that huge NOx problem was a massive step forward. But the race for cleaner shipping it's far from over. New challenges and new innovations are popping up all the time. That methane slip I just mentioned, that's the next big hurdle. While those gas engines are great for NOx, sometimes tiny amounts of unburned methane escape. And that's a big deal, because methane is an incredibly potent greenhouse gas. We're also seeing older ideas, like injecting water into the engine, make a comeback with new technology. And engineers are now creating clever hybrid systems, combining the best parts of different methods to push efficiency even further and emissions even lower. It all leaves us with this really fascinating question. As our demand for things from all over the world keeps growing, can engineering really deliver a truly sustainable future for the very machines that connect our entire world?